Here's a problem that involves universal gravitation. Space explorers land on a planet with the same mass as Earth, but they find they weigh twice as much as they would on Earth. What is the planet's radius? So to approach this problem, we recognize that weight is the force of gravity on the surface of a planet, and that force is equal to the mass times the acceleration due to the gravity of that planet. So weight is equal to the force of gravity, and it's equal to m, the mass of our space explorers on that planet, and g, the acceleration they experience due to the gravitation of that planet. So in this problem, we recognize that g of this planet, I'll say g sub p, is equal to twice g of Earth. We also note that the mass of this planet is the same as the mass of the Earth. So this increase in acceleration, or the force, or the weight that they're experiencing is due to the different size of the planet. And in this case, we can almost anticipate that the gravitational acceleration is larger, and so we expect the radius to be smaller than the radius associated with the Earth. The acceleration g of a planet, just in general, universal gravitation tells us that it's equal to capital G, the gravitational constant, times the mass of that planet divided by its radius squared. So in this problem, what we want to do is take the ratio. Well, I suppose this problem we're interested in the radius. So what we might want to do is take this expression that relates the acceleration due to a planet's gravity, and we rearrange it to present how the radius depends on g. And then what we'll want to do is take a ratio of the radius of Earth with respect to the radius of this new planet to see how, in this situation, the radii of the planet would be different. So solving for r, we'll do that up here. We'll head up here. Solving for r, we can see we have r squared is equal to the gravitational constant, the mass of the planet, over the acceleration due to the planet's gravity. I'm going to write this for the specific cases we have. We have the radius of Earth is equal to g over the mass of Earth. This is a little squirrely there. Let's write that again. The mass of Earth, and over g of Earth. And the same is true for this new planet, r sub p. And notice we haven't taken the square root yet, so we make those squared. We've got the universal constant g, the mass of the planet, over the g associated with this planet. So to solve this problem, what we want to do is take the ratio of the radius of the planet over the radius of the Earth to see how, given that the g values are related by a factor of 2 and the masses are equal, what does that imply about the relative radius? So r squared of our planet over r squared of the Earth is equal to g m p over little gp. And now we're going to take r squared over e in the denominator, so we're going to flip it. So we end up getting g m of Earth over g of Earth. And now we can see that things are going to cancel. We notice how the mass of the planet and the mass of the Earth are equal. G and G are equal, so we're going to be able to cancel those guys out. And we're going to be able to substitute in that the G value for the planet is actually twice that of GE. So when we substitute that in, we get the following expression. GP is we're going to have over GE, so we're going to have 1 over 2 GE over GE. And these guys have canceled, so this just ends up being, what we could do is we can't formally cancel those out. We get that the ratio of the squares of the radii is equal to 1/2. Let's make these smaller and make a little room here at the bottom here. So if we solve for the radius of the planet equal to 1/2 the radius of Earth, these guys were squared, so the radius of the planet is equal to 1/2 radius of the Earth to squared to the 1/2. We get the factor that relates them as just being 1 over the square root of 2 RE. And this is our main result. One over root 2 is about 0.7, so we can write this out in terms of a decibel. The radius of this planet is 0.7, the radius of the Earth. And we see that, as we expected, in order for the weight of our space explorers to be heavier on this planet which has the same mass, we expect that it must have had a smaller radius given this dependence here, and indeed it does.